Welcome everyone to the invasion of the epithelium lecture. Today's agenda is to look at how the skin becomes attacked by the invading possible pathogens, such as the coronavirus or any other type of virus, bacteria, creature that wants to get in you. If you look at your finger, go like this and feel your fingernail, and you will see that it's about, on your pointer, it's about a square centimeter. And now feel around, touch your face. I caught you there. Don't touch your face. Let me see if anyone's touching their face. No. You're not allowed, right? That's what part of the new rules. Don't touch your face. Here's the deal. There's 1 times 10 to the 10th number of pathogens, viruses, bacteria, in other words, creatures. 10 to the 10th. 1 with 10 zeros. So what is that? 100 million bacteria, viruses per square centimeter anywhere that you're looking around in the body. On the surface of your surroundings. So the skin is a first line of defense against invaders. And we say that today's lecture is going to be the invasion of the epithelium. Hold on. I just have to grab my visuals. Sorry about that. Just taking a look. If you look at chapter 15, just so we can see the images as we progress, we start the chapter with the case of the recurring chemistry nightmare. And the person, you don't know, it's a college student that's very nervous about how they look and goes to the cafeteria. And the story continues, and you don't know that it's herpes on their lips. Now, when I say herpes, that's making her self-conscious. It's herpes 1, which is a cold sore. Raise your hand if you've ever gotten a cold sore on your lips. That's herpes 1. Herpes 2 is the nasty one, right? That's the sexually transmitted one. We're talking herpes 1. And, 80% of people or more have cold sores that sit dormantly. Basically, they're viruses that sit dormantly in our lips. So we start the story with the complex situation of disease and pathogens causing worldwide trouble, including psychological. It's kind of interesting, as we talk about the coronavirus in the media, how that's turned the world upside down. And when I wrote this, I certainly wasn't thinking about the coronavirus, but I was thinking about how these little microbes cause a lot of trouble, including viruses. So let's begin by saying that our agenda is to talk about how the skin gets invaded. So it gets invaded either by physical trauma, boom, you hit it and there's a cut, by pathogens that invade one way or another, usually through a cut or an open area. Nose, eyes, mouth, any area open to the environment is susceptible for invasion by pathogens. Also chemicals. If you ever have a chemical that burns you, I once had a base burn me and it was terrible. And, so any sort of physical trauma to breach the first line of defense of the immune system, which is the epithelium, also known as the integumentary, the skin. Epithelia are tissues, and that's the most prevalent tissue of the integumentary system. The integumentary system is a system. The skin is a system, and it's your most expansive system in the body. All right, we're going to talk about the integumentary system in the next lecture. But for right now, what I want to do is talk about how it gets invaded. When tissue is injured due to the physical trauma, the pathogens, or the chemicals, it results in what we call necrosis, which is tissue damage. Necrosis is a fancy word for tissue damage. You know, lysosomes break apart as the tissue is damaged, and we call it necrotic tissue. You might hear a word like necrotic tissue. That means any sort of skin or tissue that's damaged. And what necrosis does, as all cells do, they release chemicals, and they release chemicals when they're dying that trigger an inflammatory response. So again, the first line of defense, think of the immune system as a war, and a series of defenses. First line of defense against the invading creatures like a virus or a bacteria is the inflammatory response. Most of us know, you know, what is an inflammation? An inflammation means a swelling, a flushing of an area, right? A change in the area where it hurts. So that's the inflammatory response. I call it the second line of defense because the skin is the first. Once you breach the skin, you now start an inflammation. You need inflammation. Let me tell you, the chemicals that trigger inflammation are histamine, heparin, and prostaglandins. 3 chemicals. Each do a different thing. Basically, histamines vasodilate. Vasodilation, you see this word vasodilation? That means to make blood vessels bigger. If you make a blood vessel bigger, that means you're getting more troops to an area, right? What does that mean, troops? Well, defending cells get to an area more quickly because you've made the blood vessel bigger. Let me repeat that again. Histamines are released by cells that are damaged, causing an inflammation. Inflammation, we know, means swelling and heat. What are the 3 chemicals that cause that? Histamine, up here on the overhead, heparin, and prostaglandins. Histamine, so you can even call it the chemical attack, I don't know. Inflammation is literally a chemical defense against the enemy. Histamines vasodilate. If you remember anything about histamines, they vasodilate. Vasodilation means making a blood vessel bigger. The width of the blood vessel gets bigger, which means it accommodates or carries more blood and therefore brings swelling to an area. Heat and swelling. More blood, blood is warm, more liquid makes it swollen. So now why is that important? And I just said it. Brings more troops to the area. I said that's its main result. But that's a weird way to put it. Troops mean white blood cells that defend you against the enemy. So it brings more defenders to an area. It even brings more nutrients, I mean more food, so the defenders have food to eat, and it dilutes the enemy. You know, an inflammation dilutes the enemy, makes them less concentrated, able to attack the tissue as much. Then we have heparin. Heparin is rat poison, you know. In fact, Coumadin, people who are on blood thinner, known as Coumadin or warfarin, these are similar types of bloods, types of chemicals that thin the blood. So heparin thins the blood so no clotting proteins form in an area. Now let's take a look at this cartoon of a clot. Right here, that spot is the breach of the skin. Now, you might say, why would anyone want to thin the blood in an area of a cut? Then you'll bleed to death. Well, there is a reason. Heparin comes in to thin the blood so that the white blood cells that were brought in by the histamine, the white blood cells can have an environment to maneuver. Nothing worse than being bogged down in a war where you can't move around, right? So the heparin thins the blood and allows the white blood cells to move around and defend against the enemy. Notice a clot forms around the whole larger area, preventing you from bleeding to death, all right? So that's heparin, thins the blood. I repeat, heparin thins the blood in order that the white blood cells can maneuver around. Histamine brings in more white blood cells by making the blood vessels wider. And prostaglandins do the same thing as histamines. They vasodilate, but they also give you pain. You can remember that P for prostaglandin, P for pain. Pain, why would you want pain in an area that's damaged? Well, the simple answer is you don't want to damage the area further. You don't want to rub the area because it hurts. You don't want to introduce more bacteria and viruses to the area. So prostaglandins prevent you from touching the area and give you more pain. We'll talk more about prostaglandins, which is, a chemical found in childbirthing at another time. But prostaglandins are there as well during the inflammatory response. The next line of defense is the white blood cell attack. The fancy word for white blood cell is leukocyte. You'll see that all the time on blood tests, leukocyte. And I highlighted it right here. Leukocytes are known to defend against bacteria, viruses, and all types of creatures. And I have a picture of my favorite white blood cell on page 570, figure 15.1. It's a white blood cell sending out pseudopods, which we know are fake feet that engulf the enemy. And in that picture on page 570, you got the green bacteria that the white blood cell is attacking. In figure 15.2, page 571, you might want to take a look at that. I give you an overview of the different lines of defense. Again, the skin, the chemicals, the first line of defense, then the inflammation, the next line of defense, and then we go on to the last line of defense, which we'll talk about. Figure 15.2 gives an overview of this lecture, and we'll go through all of those phases together in today's lecture, right? Just so you know where we're going. So let's go back to the white blood cells. What are the names of the two white blood cells you should know? Neutrophil and macrophage, okay? A neutrophil is like a fast tank. It rapidly gets developed and within 1 to 2 hours is deployed to attack the enemy. We find that it increases during acute infections. And we're going to talk about in one of our labs in ANP2, these white blood cells. Macrophages, and again, it's an ANP2 topic, counting the white blood cells in the blood. There's 5 types, actually. We're going to address 2 of them today. Again, neutrophils are the fast tanks leading the battle to attack the invading enemy very quickly. Macrophages develop. They take about 12 hours to develop, and they're big, large cells that really gobble up the enemy. So these are your 2 tanks. One is fast, one is slower. I would say the macrophages are more expensive to build and more powerful, but the neutrophils get there a lot quicker. We say that damaged fibers, and I think I wrote this up here, mast cells. What's a mast cell? A type of immune cell. For your purposes, it's a type of immune cell that generally travels around the blood vessels and detects damaged fibers and damaged cells and sends out chemicals. And one of the chemicals they send out is a chemical to attract these white blood cells. And again, these white blood cells carry out phagocytosis, which we discussed in the 2 lectures ago, is the engulfing of the enemy. Here's a picture of the leukocyte. It's just any old, I just drew a picture of a white blood cell. You have a better picture on page 570, but what the heck. If you take a look at page 581, table 15.1, again, page 581 of the text, there's a neutrophil, a basophil, a monocyte, an eosinophil. These are some more of your white blood cells. I want to say that your macrophage comes from monocytes, all right? So I don't want to misspeak. It doesn't matter. I mean, I'm not going to test you on that right now, but I want you to know that your neutrophils and your monocytes are kind of your next line of defense, defending through phagocytosis against the enemy. Now, what the macrophage does that's interesting, again, I said the neutrophil is the fast tank, the macrophage is the slow tank. The macrophage gobbles up the enemy and presents, like a foreign flag, proteins of the enemy on its cell membrane. We call it macrophage presentation. And during that time, you've got to realize that macrophage tells the rest of the immune system who the enemy is. You know, so if you're the coronavirus, this is how you fight the coronavirus, for example. A piece of the coronavirus is placed on the macrophage to tell all of the rest of the immune system that we're going to talk about, this is who your enemy is. Okay, so the macrophage presents the enemy. And that causes more white blood cells to go to the area and know who to attack. And that brings us to the specific line of defense. Specific line of defense. What does that mean? Well, that means you're going to target specifically the enemy. You're not just going to gobble up through phagocytosis anything that moves. It's a targeted attack like sending a missile. And if you look, antibodies are the creatures that are involved in this specific attack. And this is your last line of defense. We say that there are circulating B cells that make antibodies. What's a B cell? Let's go back to page 581. There are B cells and T cells. All right, I gave you a picture of either. They're not that exciting in the picture, you know, but just so you know, I'm not making it up. There's your B cell. And B cells come from something known as lymphocytes. Lymphocytes are a type of white blood cell. And they circulate. And when the macrophage presents the enemy flag and says, this is the coronavirus, for example, this is who you need to attack, the B cell produces antibodies against that particular virus, or antibodies against a particular bacteria or even fungus. So antibodies are made specifically to target certain invaders. Let me highlight that. Antibodies are made to specifically target certain invaders. And I want to say they look like airplanes. And I'm going to say they look like airplanes. They look like airplanes. Take a look. There's little wings and a little cockpit, and the little person sits in the cockpit. I'm kidding. No, but there is little wings, and then there's like a cockpit area. There's light chains on the outside, heavy chains which hold up the whole structure. And at the ends of the heavy chains, there's little variable groups. What's a variable group? It means something that changes for every little antibody. Every airplane, let's say, is made specifically against a particular invader. So let's again visualize. Let's go back. Take a look. You got your macrophage. Everyone look on page, I want you to look on page 582, figure 15.10. That's how a neutrophil and a macrophage works. If you look at the picture, and I don't want to show it up, like, you know, here it is in the textbook, right? That's phagocytosis. The enemy is eaten up, gobbled up by the neutrophil or the macrophage, gobbled up to attack the invader. But what the macrophage does that the neutrophil does not is that it presents the antigen. And if you look, go to page 585, figure 15.13, and it says a macrophage presents the antigen that it engulfs. It then places the antigen on its cell surface, which attracts T helper cells. Whoa, what's T helper cells, Demflay, you're probably saying? That's another cell that activates the immune system, the specific attack. All right? That's what activates the B cells to make antibodies. Do you have to know T helpers right now? Absolutely not. If it's not in the notes, you don't have to know it. But I like to give you a full flavor of what's going on. Now listen to me. Macrophage presenting the invader. Macrophage eats up the coronavirus. A piece of the coronavirus is placed on the surface of the macrophage, which gets B cells to make antibodies, right, against that coronavirus. It's those antibodies, this picture of the antibodies, all right, I repeat, it's this picture of the antibodies that I want you to know in terms of immunity for the coronavirus. If you get the coronavirus, you're going to have some degree of immunity, unless this virus acts different than any other virus, and I don't believe that's the case. You're going to have some degree of immunity, and we have noticed that there's varying amounts of antibodies in people. I don't know of any cases of people getting the coronavirus and then becoming reinfected. Those were false reports. There's a lot of misinformation out about the coronavirus. And I'm not saying I'm an expert. Let me throw that in. You know, I have my degree. I mean, I'm more of an expert than the average, I'll tell you that. I mean, I have my degree in microbial ecology. So, I mean, I know my stuff. But I want to tell you that you are immune, as far as we know, once you get the virus. And those antibodies can be used as a treatment for treating people infected with the coronavirus. And so far, the studies are showing very promising. And I'll leave it at that. So, you know, it's interesting about the antibodies. Let me tell you how they work. They specifically target invaders by making them tasty. It's known as opsonization. They coat the enemy so that more macrophages can attach more easily, and we say it makes it more tasty for the macrophages. That's a good word to talk about at the dinner table. Opsonization, to make tasty. You can tell your parents that. Wow, you've really opsonized this meal, Mom. Then she'll be a lot happier with you being home from school, right? Anyway, a little humor. Let me see if anyone's laughing. Absolutely not. I don't see any faces. You're probably grinning a little bit, maybe. Opsonization, you know, say that to yourself, opsonization. So anyway, all right. So what are the 4 roles of the antibody? Okay, neutralization, agglutination, precipitation, and complement. Those are the 4 ways in which an antibody works. Please turn to page 588 for a picture. 588, figure 15.16. That is a picture of neutralization, agglutination, precipitation, and complement, and a picture of the antibody. As you can see, a fancy word for antibody is immunoglobulin. You should know that they're synonyms, okay? Because if you read the literature, you'll hear immunoglobulin, and if you talk to the average doctor, they'll say antibodies, okay? But you got to know that they mean the same thing. Now let's take a look at what each of these words means, all right? Neutralization means masking the dangerous parts. If you look at the picture, you can see neutralization, like muzzling a dog. You got a nasty dog, you muzzle it, you keep it from biting. That is what an antibody does to some viruses. I don't know what it does to the coronavirus. I'll tell you right now. I stopped reading into the real details. It was making me crazy, all the misinformation. But, you know, neutralization is one method by which we stop a pathogen, you know, an invading creature. Agglutination is the next one, clumping them together. And that's the next one. A certain type of antibody pulls a bunch of antigens together. Again, antigen is another word for enemy, pathogen. So you might want to write that down on your notes. Pathogen equals enemy, equals virus, equals bacteria, equals antigen. So these are all words that we use interchangeably. The enemy is clumped together in the second physiology of antibodies. Why clumping them together? Because clumping them makes them easier to attack, right? You can attack your antibodies, you can attack your enemy a lot better if they're in clumped groups than if they're spread around, which is why, I mean, I hate to say it, the virus attacks us that way. How come New York City got hit and all the cities and the rural areas less? Because we're all clumped together and they can spread, the little virus can spread more easily. The virus uses its tactics against us. We use counter tactics against them. Okay, keep that in mind. And if you think in a war, you know, where do they bomb? Usually a city. So where people or viruses are clumped, that's where you go after them. So agglutination makes sense. Precipitation, everyone. Let me ask you this. Have you ever had a friend who's not really a friend? You know, have you ever had a friend who you thought was a friend? Sky, you're the only one on there. Go like this if you did, and go like this if you have not. Did you ever have a friend who you thought was a friend, and then they turned on you and weren't really a friend? Thumbs up that you did have it. Thumbs down means you have not had it. Oh, let's see. You did not. You're lucky. Boy, I'll tell you one thing. One of these, oh, Tanya had one. Sky, you're going to have to talk to Tanya after lecture about a friend who's not really a friend. I had one definitely at the college, and they'll gossip about you, tell stuff, and make stuff up. You know, you tell them stuff. Very bad to have a friend that's not really a friend, right? They can really bring you down. So that's what precipitation is. Precipitation brings out the enemy that you didn't think was there. You know, an enemy antigen, you know, virus, whatever. If you don't know it's there, you're in big trouble, just like a friend who's really bad. You don't know it's there, and you're going to get screwed over. And here's the deal. Precipitation finds the liquid soluble antigens and brings them at a solution. In other words, just like bringing friends that are bad out into the light, precipitation precipitates out or takes out the enemy from being dissolved to being clearly present in the blood so that the immune system can attack it. I love the precipitation analogy because I've suffered terribly from bad friends. I've had some good friends, I'll tell you that. But definitely, you know, I can think of one that was really, I mean, it's crazy. Just, you know, they thought, you know, you thought they were your friend and then they forget it, turn on you. But, you know, so it goes in life, Sky, as you know, so it goes. So anyway, Tanya, I'll have to hear the story at some point. But I guess online is just, we can't do it online and recorded. Can we now? And open to YouTube. So we won't. Let's move on to compliment. Compliment is not, those are nice shoes you're wearing. Compliment is a series of reactions in immunology that lead to a certain goal. And if you look at the picture on page 588, it says complement. By the way, complement should be spelled with an E, not an I. That's my typo. 1 point off for me. Complement is a series of chemical reactions that occur on the cell membrane of an enemy and literally blow chunks or blow holes in the enemy. All right. So again, why don't I reiterate to everybody? These are the 4 ways in which an antibody works. Neutralizing the enemy, clumping them together, bringing them out of solution so you can see them, the evil friend, and complement, just blowing holes in the enemy through a series of chemical reactions. All of this time I spent is important because I want you to understand how an antibody works. That's how the coronavirus antibodies work to attack the enemy. And there's no doubt to me that antibody treatment will have a positive effect. You know what it is with the virus? Science takes time, you know, and I don't want to get into it too much. The media corrupts it, but science does take time to come up with solutions. And last but not least, we have cleanup. Cleanup is, you got to clean up your mess afterwards, right? So macrophages phagocytize or gobble up the enemy. The dead tissue is pus. If you have pus coming out, which is, you know, I mean, this is a disgusting conversation, but creamy yellow, dead tissues, pathogens, neutrophils. A pimple is like the sign of heavy battle, right? Pus coming out. Dead tissues, white, you know, fibers, white fibers, yellow fibers, all that stuff is part of the cleanup. So macrophages clean up the mess at the end. And pus is an indication, and I have a picture on page 583 of some pus coming out of a finger's abscess. And pus means that the war is over, and, you know, pus can be infectious, though. And pus is infectious, and there's still some dead and some half-living enemies in there. An abscess is a failed inflammation that's walled off literally by the body, you know, wall of collagen fibers, because the body gives up. The body's like, hey, this was a bad battle, so we're just going to close up shop. And really, the abscess has to get lanced. And I have a picture, or at least, you know, opened, the pus removed, and either antibiotics, sometimes not antibiotics, to, you know, heal the situation. And I'll tell you a story. Many years ago, I never had a plastic surgeon in my life, but I was lecturing on the skull. It was a very stressful time where I was writing, you know, writing my books. It was in 2012, I think. Yeah, fall semester 2012. And I just, you know, had this nasal infection for a long time. I mean, it went on for weeks, you know. And Well, to make a long story short, I just felt a bump right here. And I said, this is not good. And it was an abscess. I knew it was. And it had to be lanced. And it was a big, had to be rushed to Cooperstown Hospital, or rushed myself. It had to get done, or I just wasn't going to get better. And, you know, so I had to have, you know, shots in the face and to numb it. And they went right up here and they lanced the abscess. And it was scary. I was awake. And, you know, the surgeon had a little sense of humor. He knew I was the anatomist. And as he went in, he said, well, if I go just a little more, I can suck your hypothalamus, your pituitary gland out, which you don't want, obviously. It's a part of your brain. He was messing with me while he's doing the surgery. He was actually very good, very efficient, and it was a total success. My whole face was blown up and just swollen. It was really quite luckily I had a student there who, they forgot my antibiotics. He ran out and gave me my antibiotics. So I had a student from way back. He did pass just by half a point. Thank God, by the way, he passed by half a point. He was pretty good. Anyway, to make a long story short, that was vicious, a vicious little abscess. So abscesses can be dangerous if they burst and infect the rest of your body. So for example, like with me up here, it could have burst and, you know, it can go to your brain. So nothing to sneeze at. No pun intended. That's a bad joke. All right. 2 words you should remember. Mr. Pimples and Mr. Tooth Decay. This is a micro topic, but I think an anatomy student should know this because these are the creatures that want to invade you. Staphylococcus means a cluster of round bacteria. They look like grapes if you look at them under the scope, and you have a ton of staph on your body at any one time. I told you. You know, 10 million bacteria per square centimeter. And I just want to say that's Mr. Pimples. When the staph gets into your hair shaft, and that provides a warm place for the bacteria to grow, we call it a pimple, right? That is literally a small infection by Staphylococcus. And then we have the bacteria that I did my own research on, my bachelor's thesis. You know, touch your teeth. Streptococcus. Strep means a chain. Coccus means round. So a chain of round bacteria is Streptococcus. Mr. Tooth Decay. Strep, you know, you have strep throat. Strep can affect your heart valves. Strep's nothing to sneeze at, and it does cause tooth decay because it makes acidity and makes holes in your teeth. So Streptococcus is what I did my own research on, looking at different types of Streptococcus strains, all right? I studied Streptococcus mutans, Streptococcus subrinus, and I saw the effects of fluoride on the different types of these bacteria. That was my research. Taking spit samples from little kids, that's not fun. I almost went to dental school, got into dental school, got a scholarship, and I said, well, either the PhD or dentistry. That's a little bit of my own history. So I can give you, that was tough too, because I'd have made a lot more money otherwise. But this is fun, right? You know, I could be drilling your teeth. That might be fun too, right? No way. All right, moving along. So that, everybody, that is the various lines of defense and the cleanup of the immune system. Why don't we talk about tissue repair? And let's take a look at page, I have the tissue repair right here. Let's do page 580. Page 580, figure 15.9. It shows the types of repair, or the process of repair. Sorry. Okay. If you see the mast cells circulating, right, and then you see the clotting factors, and then you see the phagocytes, and then you see letter D, the actual fibrosis. And letter D is what we're addressing. When you repair tissue, there's two types of tissues you get. You either get scar tissue or you get your tissue back, right? So if you cut your hand, you don't want there to be a big scar. right? That's called fibrosis. Fibrosis is the replacement of normal tissue with scar tissue. And scar tissue is nothing but fibrous connective tissue, everybody. And that is not the same as your skin or the original tissue. So regeneration, the word regeneration is what the goal is, to get your tissue back to the way it used to be. And if you go on page, skipping around here, I have a little chart. Let's go to page 591, figure 15.18. If you look at that, that's a list of different types of tissues, and it shows regeneration based on those types of tissues. And in the new edition, I'm definitely going to put a bigger picture of that, because that's really important. That's why I'm doing a second edition. I have various little things I want to do with this. And regeneration, let's first discuss what the process of regeneration is. First, fibroblasts, which are circulating cells, all right, that blast out new fibers, lay down a network of collagen fibers. And then scar tissue, also known as granulation tissue, forms by capillaries invading the area and laying down, you know, through the fibroblasts, scar tissue. So you have scar tissue. The pro of scar tissue is that it's infection resistant. Most people don't know that. You cannot get infected again if you are scar tissue, all right? And, oh, question, are the textbook pages on the syllabus? Yes, yes, textbook pages are in the syllabus. So you can read ahead and all that. Okay, so I just was checking my chat room. And another person gave a thumbs up. Hold on. I have to stop for a second. Imani has 6 thumbs, so she had 6 friends who betrayed her. Well, this would be a real good conversation. We can open it up to conversation. I'll shut off the recording at the end. Listen, infection resistant. If you think of scar tissue, you got to think of like politicians. They always go overboard, even with the coronavirus, right? Everyone goes overboard. So the body goes overboard when it gets cut or has damage and makes scar tissue, and a lot of it, and makes it so that it's infection resistant. The con is that it's not functional. If you have a heart attack and you have scar tissue in the heart, right? That tissue is not functioning like a regular heart. That damages the heart's functionality. That's a big reason for, you know, heart failure. You do not just want scar tissue. On the skin, who cares? Even though it's ugly, well, it's not the best. Like if you have large scar areas, they're not going to behave like regular skin, not going to sweat the same, not going to feel the same. So I guess what I'm saying is scar tissue has the pro of being infection resistant, but the con of being not functional. It does not function. So what is the goal? Regeneration. And regeneration is another word for mitosis, replacing the network of cells that you once had. So you damage your heart, you want it to regenerate. You see the word regeneration, that means returning it to the way it used to be. I'll tell you, skin is very easy to regenerate. When I had my abscess, he said 72 hours, it'll be healed over. And the man was right. The plastic surgeon was right. And I mean, I knew that anyway, because I'm an anatomist. It takes 3 days to heal over. You know that from a scab. So epithelial, because it's cheap to make epithelial cells, and you'll see about the skin in the next lecture, it's kind of cheap to make these flat cells, right? We talked about epithelial. They're really easy to heal. So skin's easy to heal. Bone has a lot of blood vessels. Remember I said in the last lecture? A lot of blood vessels mean you can bring a lot of healing cells. Everyone, bone heals in 6 to 8 weeks. Isn't that beautiful? Now, unless you you break your bone, it's great. Unless they set it wrong and you get infected, it heals in 6 to 8 weeks. And I think that's miraculous. You screw something into it, and we say that it ossifies. Another word for bone healing is ossifies. And we're going to do a whole lecture on the bones, okay? And I know you have quite a few labs on bones after the practical. Areolar heals easily. That's just the cushioning tissue. Remember I told you that? The dermis, or underneath the skin, dense, irregular, that heals easily. Obviously, blood heals easily. Now let's talk about moderate healing. The more expensive the tissue, the harder it is to heal. What do I mean by expensive? The more complex it is. If your Cadillac breaks, it's a lot worse than if your, cheap Ford Taurus breaks, right? And I had both cars. I'll tell you that. I had both cars. Cadillac and Ford Taurus. And I don't know which one I like better. Of course, a Cadillac, you know, everyone, I don't care how, if everyone thinks I'm 100 years old driving an old Cadillac, I'm telling you, people still look and say that car is fantastic. But when it breaks your bank book, right? Because it's expensive. The parts are expensive. It's a Caddy. That is the same as tissues. When it's expensive to build, like cardiac and nerve tissue, it is hard to heal. Because as we talked about in the last lecture, right, you have all the striations, you have the nerve tissue that are little wires. These are expensive, specialized tissue, hard to heal. It doesn't mean they don't heal at all. Cardiac and nerve, right, heart and nerve do heal a little bit. Peripheral nerves take 2 years to heal. Did you know that? So if you cut yourself and you cut a nerve, it may never heal, but it takes 2 years to heal. Very slow process. Heart, get a heart attack. There is some evidence that there's some healing. It's not nothing. Now, let's talk about dense regular, which is, you can write next to that just so you remember, ligament and tendon. Ligaments and tendons have moderate healing. They're not great because they're also not cheap to make. There are a lot of parallel collagen fibers, right? Smooth muscle too. But they will heal. If you rip, you can just, you know, a golden rule of thumb. I always have a rule of thumb. If you rip your tendon or ligament more than 50%, you're going to need surgery. Okay, if it's less, it can heal. The more it's ripped, the more you're going to need surgery. Then let's talk about poor to moderate skeletal muscles. You know, your regular muscles like your biceps, triceps, you don't want to rip them. They have a poor healing ability. Also, cartilage. Cartilage. I told you a fool and his cartilage is soon parted. You got to think of cartilage as an eraser. And, right? Because an eraser is at the end of a pencil. Cartilage is at the end of your bones. Remember we talked about that in the last lecture? As you wear it away, you don't regenerate it. Very poor. Why not? It's mostly water. It's avascular. There's no blood vessels going to it to really bring healing and regenerating cells. So you cannot make a new network of cartilage. I've never heard of cartilage healing and rebuilding. That's what I mean. I've never heard of it rebuilding. Glucosamine chondroitin does not work. I've heard about dog studies that, you know, that the dog feels better. It's just there's no evidence that it works. Cartilage has to be replaced, and I'll talk more about this when we do the orthopedic unit coming up actually next week. And I'm just saying that that's the reason for about 600,000 surgeries a year. Neck, back, hip, shoulder, knee, all of that is the wearing or damaging of cartilage. And cartilage is your cushion. It's the eraser at the end of the pencil, the eraser at the end of the bone. And it cannot just regenerate willy-nilly. Now, if they could do that through stem cell research, wouldn't that be grand? A lot of surgeries would be gone. So then I ask you, you know, a rhetorical question. Is taking anti-inflammatories, antihistamine drugs good or bad? You know, I'm not going to ask you that question. I'm just going to say, you know, it has pros and cons. You reduce the inflammation, and sometimes too much inflammation causes damage. And on the other hand, you're interfering with nature's response. You need inflammation to attack the enemy. I had a friend who got the coronavirus, and her mom's 92 and got it just 3 weeks ago. And they say, you know, and here's more of the misinformation. Take ibuprofen to lower the fever. Don't take ibuprofen. You know, still that's all out there. And she was okay. She had the chills. She had an inflammatory response. You know, the mother was okay. No problem. The husband had no symptoms at all. And I had another friend who's with the coronavirus. And I bring this up for a reason. The complexity of invaders and everyone's immune system. We don't understand it fully. But his uncle is dying of cancer, in bad shape, got the coronavirus, no problem. His uncle's wife, I guess it's his aunt, is in totally good health and got the coronavirus and is dead. So, you know, these are rarities. I mean, you know, I think you're going to start seeing the death rate from the coronavirus equivalent to the flu. If you add it all up, 0.1%, that's what you're going to see. I think that's what you do see. And I knew that when it was in China, and I looked at the data all the way in January. I've been tracking this. And I told the students that, you know, in the fall. But nonetheless, it freaks you out because it is, you know, because there's death. But there's death from the regular flu. So it's an interesting dynamic. And why do I bring that up? The haphazard death and why it affects some and not others? Because all part of immunity. How does your body defend against the invader? This is more complex than I'm leading on. This is only your first lecture. But as you become an expert in this field, you will see that there's a lot of factors involved. And I find it a fascinating area. I love teaching this as it is like a military attack. And I wanted to show you a little chart. And it's in a different chapter, and it's not really going to be tested, but I thought it was interesting for you to see. It's in the virus chapter. Let me show you. It's chapter 8. There it is. Turn to page 279. I think it's interesting, the pie chart. And this is, again, not on your test. Page 279, the pie chart. Whoa, it shows you, this is way before, you know, this is like 5 years before the coronavirus. I wrote this book. And that's why I'm doing the new edition. And it says influenza outbreaks occur due to mutated strands of the myxovirus. In the 20th century, there were more U.S. deaths from the 1918 flu outbreak than due to all the major wars combined. Vietnam, Korea, World War I, World War II. Throw in the Persian Gulf easily. Throw in everything. I mean, and look at the pie chart. Way more worldwide, 30 to 50 million died of the Spanish flu. And, you know, they really didn't do anything about it. We didn't shut down. Nothing was done. I want to also add that the flu kills an average of 36,000 people a year. I believe last year was particularly hideous with like 90,000 dead of the flu. So I want you to get things into perspective when we look at the number. We have about 110,000 dead in the United States from this flu. Obviously horrible. Nobody wants it. But it's interesting to see 1 million Americans died 1918 from that flu. 1 million is a lot more. That's, what is that? 10 times more. So one wonders about things, what the right response should have been, could be, will be, don't know. But nonetheless, we live in an interesting era. I'm going to stop recording because I just want to